Today we will be discussing about the properties of normal distribution. So the first property or some of the properties are included in the moments of the distribution. Before moving on to the moments of the distribution, I would like to introduce you to the term what a moment is. So moment are statistical measure used to describe the characteristic of a distribution. Now, I hope you all know about, you have all studied the measures of central tendency, and the arithmetic mean and variance are the first two moments. They are used to describe the central tendency and dispersion respectively. So here in this case, as I said, the arithmetic mean, or you can say what mean, simply mean, is also known as, when in terms of moments uh, you can tell it as, or you can name it as first row moment. Is in the case of a normal distribution, it is denoted as mu, a Greek letter, and the variance, nada moment, which we say it in the terms of moment, which we usually say it as the second central moment, and it is denoted by sigma square. Then the fourth central moment is denoted by 3 sigma raised to 4. Now, in the case of normal distribution, so if it is any other distribution, all these values will be changed. And in the case of a normal distribution, the odd moments are always 0. Okay, so that is why I didn't mention about the third central moment. Now let's move on to the skewness of a normal distribution. So before moving on to the skewness of the normal distribution, here again I would like to give a small idea of what skewness means. I hope you know the word meaning of skewness, but yes, if the data are distributed the same way on the either side of a central value, the distribution is said to be symmetrical, otherwise it is said to be skewed. I hope you all know how the graphical representation of a normal distribution looks like. It is a bell-shaped, and it is clear that with when you view that graphical representation of a normal distribution, it is symmetrical in its both the sides of symmetry. So so there is no skewness in normal distribution. The skewness is 0 in case of normal distribution. The shape of the frequency gives us an indication of the skewness, as we say, and the shape of the frequency in case of normal distribution, as I said before, it is symmetry, and the skewness is 0 in this case. Now, yes. Now, in normal distribution, as I said, the skewness is 0, and the measure of skewness is usually denoted in any other distribution also. It is denoted as beta 1, and in this case, in the case of normal distribution, beta 1, or the measure of the skewness, is equal to 0. And hence all the odd moments are all 0 that I have earlier quoted. And in this case, I would like to also mention that the mean, median, and mode, in the case of a normal distribution, mean, median, and mode coincide. So next we will move on to kurtosis of a normal distribution. Now, before moving on to the kurtosis of a normal distribution, let's have a look at what the term kurtosis means. Now, kurtosis indicates the peakedness or the heaviness in the tail of the frequency distribution, graphical representation of what the data that you have got. Now, usually kurtosis is denoted by beta 2, and in the case of a normal distribution, the value of beta 2 is 3, and that is why we say that the normal distribution is a mesokurtic. And let's have a look at what is actually meant by mesokurtic. Now, if you have a closer look at this figure, you can see that there are 3 bell-shaped curves plotted over here, and the lighter pink one is named as leptokurtic. It is the peak, it is very it is the width of this curve is very small compared to the other two, and its height or the peakedness, when we measure it, it is it's greater than the other two. So when we measure it, we usually get that it is greater than 3, and hence it is called as a leptokurtic curve. uh, Again, normal distribution is not a leptokurtic curve. We know that beta 2 is equal to 3. And coming on to the black curve, here it is named given as normal. Actually, this is the figure, or this is the graphical representation of a normal distribution, and this is known as a mesokurtic curve, since this is actually a perfect curve, bell-shaped, perfect bell-shaped curve. And here when we measure, we get the kurtosis as beta 2, or the measure of kurtosis beta 2 is equal to 3, and hence this is a mesokurtic curve. So normal distribution is a mesokurtic curve. And when coming on to the red graph, here the red bell-shaped graph is a little bit flattened when compared to the other two, and it has a larger area compared to the other two, and it is called as a platykurtic curve. And here in this case, the measure of kurtosis, that is beta 2, will be less than 3. In the case of leptokurtic curve, beta 2 will be greater than 3. Now let's have a look at the inflection points of the normal distribution. Again, I have shown here the bell-shaped curve of the normal distribution, and the curve changes its shape at 2 points like this. Okay, so the 2 points where the curve changes its shape is known as the inflection point. Usually there are 2 inflection points in a normal distribution when we plot, since it's a bell-shaped curve, and the inflection points are exactly 1 standard deviation on each side of the mean. So the mean lies somewhere over here in this point, here in the peak point, and if you draw a line from this to 1 standard deviation, and from this to 1 standard deviation, if you draw a line, this is the inflection point. And as you can see, the mean is mu. So on the either sides, it's clearly said that it's exactly 1 standard deviation on each side of the mean. So moving on to the positive side, it will be mu plus sigma, since sigma is the standard deviation. And moving on to the negative side, it will be mu minus sigma. Sigma here indicates the standard deviation. Also, we have to look at the area of this graphical representation. Now, if you take this bell-shaped curve, that is a normal curve, 68.26% of the area or of the data is contained in this area. Okay, the area between mu minus sigma and mu plus sigma. Again, 95.44% of the area is between mu minus 2 sigma and mu plus 2 sigma. 99.74% of the area is between mu minus 3 sigma and mu plus 3 sigma. So that's regarding the area of a normal distribution. Then another remarkable property of the normal distribution is it stated in central limit theorem. So what is central limit theorem? As n increases, or as the number of sample size increases, the distribution of the mean, that is the distribution of mean, that is what x bar of a particular random sample taken from any population. It's not necessary that it should be normally distributed population. No, it could be any that population can follow any distribution, but as n increases, as the sample size increases, the distribution of the mean, that is x bar, approaches a normal distribution. We have a theory behind this, but it's not necessary to learn it right now. So just you just have to remember that this is an important property of a normal distribution. Thank you.